All right. There's only one meeting going on. Everybody managed to make it to the new one, hopefully. Looks like I'm missing someone. Oh, it's Kayla. All right. All right. So let's get started. And I just slightly change the arrangement here. I just noticed there's a one page in lesson 59 that refers to the topic from 60 because they can be taught in sort of either order. So I'll do this one first so that when we get to that one, it makes sense. So we're looking at interference due to diffraction and so on continued. And we're going to look at, instead of just two slits, we're going to look at multiple slit systems. They're commonly called diffraction gratings. Actually, I think I will just go with this one first because I want you to see the diffraction stuff first hand before we do this. Does anybody did anybody track down a laser pointer at all? I want to know if I'm helping anybody walk through the demo or not. No one has a laser pointer, apparently. Okay, so I'll try and show you on from this end for sure, obviously for everybody. So as we looked at before, when we look at our finger and our thumb super close together with a light in the background, and if you hold your finger and thumb super close to your eyes too, it's even better, but you can actually see, of course, diffraction there. We saw like the darkness sort of grow between your finger and thumb before you're actually touching. And also, if you look super close at the details, you can see an interference pattern. So a bunch of lines that are parallel this way to the surfaces of your finger and your thumb. So, you know, the question that we're starting to look at now is like, okay, why would there be an interference pattern if there's only one slit? Yesterday, we went through full detail of how you can have an interference pattern with two slits, and it's fairly simple to go through. I'm just trying to find the actual lesson here. Two slit interference pattern math. Just load the PDF because it loads nice and quick. So we talked about how, you know, you have light coming from this source and light from that source, and because there's going to be a path difference between the two, you can end up off by either a full wavelength, in which case you'd have constructive interference in a bright spot, or you could be off by half a wavelength, in which case you'd be having destructive interference and have a dark spot. So it's very easy to analyze and, well, easy to understand. And then the analysis, of course, ended up being a bunch of math that led to a bunch of new tools for us to use or new equations for us to use, right? But the concept is super simple. You have just these 2 point sources that are identical, and they're either arriving in or out of phase. So they're either constructively interfering or destructively interfering. So the idea is pretty simple. Why are we getting an interference pattern with a single light source, though, is very strange. And I think a lot of people don't even realize it happens at all. You'll see in a reading later on that I go through. It's not in this lesson, but later on I'm going to be reading from a book for some other applications that some other concepts and let's say historically, scientifically significant results and experiments and so on that I want you to understand. I'll be reading from a book that helps understand. And there's a spot where it's kind of wrong the way they rephrase it, because they say that if it was a single slit, then you wouldn't have an interference pattern. And it's like, well, actually you do. So this is the DIY demo. If you manage to get your hands on a laser pointer at some point, and 2 pencils and elastic band should be the easier part to track down. If you shine the laser light through the 2 slits, we can get an interference pattern for ourselves. So Kayla, where are you? Where's my phone? Okay, sorry, we're just working out technical difficulties here to make this happen. And so maybe I'll go to, can you share the, can you put the camera on there, Kayla?
Oh shoot, I turned it off.
Oh.
I'm sorry.
Technical difficulties still happening here.
Okay.
1 second. It'll be worth it.
Okay.
The
camera's on.
Here. Don't see anything. Can anybody see anything?
Oh, I can try and like spotlight.
Oh, I think I have to spotlight you, maybe, unless you can spotlight yourself.
I'll try.
Organizer.
I don't think I can.
Wouldn't it be easier if you logged in on your phone? Because I don't see myself logged in twice here. That doesn't make any sense. Word. Go get your phone and then. Sorry, we're trying to figure this out. I tried to get her to use her phone and she's like, no, I'll just. Anyways, for now, I'm just going to turn my camera on. Remember, we have the pencils, and I'm going to be shining through. But I need to be able to show the result on the wall far away. That's why I want her to be able to get her camera going so she can show it far away. But I'm just going to be shining the laser through the two pencils, and you're going to see the result on the wall. So get your camera on. We're actually going to show the result up on the wall up at the kitchen. So Kayla, and I can spotlight Kayla. Waiting to see the screen. There we go. There's Kayla's forehead. All right, there's the stairs. And if I put my camera on, can anybody at home, can you see me and can you see both screens like I can right now? I guess so, right?
The stairs are bigger and then your face is small.
The mess I have here. Okay, good. So Kayla, point towards the upper on the wall in the kitchen. All right, so you can see what I'm doing here, and you can see the result up there. So Kayla, up here, see where the green dot is?
Yeah, I got it. Yeah, I got it.
All right, perfect, good. So this is when it goes through between the two pencils, and you just need Kayla to zoom in on that there. And steady. So see the interference pattern there? Okay, so if I squeeze the pencils, the interference pattern changes. So if I don't squeeze, it's a thinner, it's a wider gap, I should say. And then as I squeeze the pencil, see how it spreads out. But look at the fact that you're getting all these dark and light spots, right? So the bright, wide green center. Notice that center section is like twice as wide as the rest of them or so. And then there's those spots where we've got dark spots lining up. This is just the laser pointer itself, just shining. Sorry, I'm a little jiggly here. That's just the laser pointer. And then when I go through the pencil slit, we get diffraction interference patterns. So that is diffraction through a single slit. All right, so we're done that. Let's go back to normal here, stop spotlighting, and so on. But so to see it firsthand-ish is what I wanted you to have at least an experience of there. And so that's the far away screen. The farther away, the better. So I was downstairs, as you sort of caught what's going on here, and then way up the stairs, upstairs, across the house. So a good probably 40 feet away or something on the wall. And that just helps the pattern that you actually are producing spread out. So if you're ever trying this and you try and just shine it through and shine at the wall in front of you, you can still see it. You definitely can actually still see it, but it's a little harder because it's just not spread out. So I can probably show actually here my camera version of this. I'm just going to go in the ceiling here. So this is the result I'm getting on the ceiling. I don't know if you actually, you can't really, my camera's not good enough to be able to catch what's going on there, I don't think. anyways, unless you were to look at the big version of the picture, which I don't know how to get to do that right now. So we're done. All right, so that part. So yeah, anyways, it happens, right? So this is what we saw. The single slit interference pattern, we get this like wide center section of constructive interference, and then destructive interference on each side. And so, we're saying like, how is this possible? We only have one light source. Doesn't make any sense to us. Plus the fact that, now we can look at that double slit interference pattern. And people describe the double slit interference pattern as just a bunch of evenly spaced dashes. But there's also this extra detail of, evenly spaced dashes, but then we've got sections where it tapers off to nothing, and then it gets brighter again, and so on. And what you actually have is a combination of both of this. Like, see how they're related to one another, right? So if you look at this bright center section, well, that's obviously that bright center section, but then it has dark spots. So, what you have going on, I'm going to be showing soon. Where is it here? I'm going to try and show the two patterns overlapping. I'm just getting ahead of myself. I want to try and show. Where is it? Well, anyways, you'll see it in a slide eventually here. I lose my organization as to what things are. But if I just do a quick screen capture of this right here, it's kind of a weird thing where it's like with a single slit pattern, you have that, right? And then with a double slit pattern, you're getting really actually two of these things overlapping. Okay, so two of them overlapping, like right over top of one another, like that, right? And so as a result, we're getting destructive interference, and you see this little square down here says, notice that even though with the double slit interference pattern, twice as much light's getting through, right? But now there's dark spots. So picture like, there's these two patterns, and if they were, above one another, they'd be like that on the wall. And then when they overlap, they become this pattern down here. It's kind of strange, right? So you can tell there's destructive interference going on, and the question is really why, right? So let's do this. I'm going to say like this plus this plus sign and equal sign, and there we go. Go white. There we go. So this plus this equals this, right? Is kind of to make it obvious what's going on here. And you'll see something like that again on a future slide. We had noticed this other pattern in the dark and bright bands, but if you're reading more about this places, you'll quite often hear people refer to the double slit pattern as just a bunch of evenly spaced lines, and that's it. They gloss over, I think, just because they don't want to talk about the complexity of it or something, but they sort of gloss over the fact that there's actually a pattern as well as the double in the double slit pattern, right? There's this other pattern of just instead of a bunch of evenly spaced bright and dark bands, there's also these like, this center section that's bright, and then it goes dark, and then it goes bright again, and then dark, and then bright again. Okay, and that's actually that single slit pattern that quite often people kind of ignore. So like I showed you before, right? This is the pattern we're emphasizing now, right? The center section that's bright, and then dark, and then bright again, and so on. That's the single slit interference pattern that we're talking about. Okay, so why is there diffraction with a single slit? Even water does this. It's kind of a strange thing. Even water does this. This is just a single slit here, and you've got like these patterns, right, that you've noticed before when we were doing the ripple tank stuff in grade 11. I can't see it as well here, but I think you can, use your imagination, picture there being an interference pattern there too. So, this picture, I'm not sure if it's, I'm not sure where it came from, like Google or whatever, and I'm not sure if it's like totally legit or not. But if you look there, I'm just noticing that saying, hey, that sure looks like Huygens wavelets to me, a bunch of little wave fronts, right? And that's going to be the key to us actually understanding why interference or destructive interference is occurring with a single slit. So this one looks way more realistic. So, like the idea, see that it looks like there's a bunch of ripples coming in the center there. So there's your Huygens wavelets, right? And we're going to take advantage of those Huygens wavelets to try and predict or explain why we have, these spots. Like right there is a destructive interference spot. Okay, right there, and right there, and right there, right? So you've got these spots that show up, which is kind of strange. So you'll notice the narrower the slit, the more diffraction, the interference spreads out, and it's not as noticeable. So this looks like nice circular lines at this point, whereas this one, there's those ones, there's more interference visible. And that's kind of what happened in the video too earlier, right? When I was doing that, when I squeezed the pencil, the narrower the slit, it kind of spread out, and it was harder to notice the pattern once it spread out too much. But yeah, so we're getting these two patterns, right? A single slit and a single slit, adding up to be this double slit pattern, as we've mentioned. So there's supposed to be an applet there. You can play around with it, but so this one still works. We'll leave. So I can change this to a single slit, and then I can play around with the slit separation, or not slit separation anymore, but I can play around with the slit width at least, right? So as I'm going to a, like right now, you wouldn't even notice there's a pattern, of course, right? Because it's too wide. The slit width is not the right value. And so now we're going wider and wider slit, and you can see that it's compressing the pattern. Okay, so when I squeezed the pencil, it was like it spread the pattern out to the point where you couldn't even see any pattern, and so on. So this is what you're looking at. So there's that double wide section, or approximately anyways, and so on. Yeah, this one doesn't work anymore. Oh, by the way, this is where we said the narrower the slit, the more diffraction, the interference pattern spreads out, as we said before. So this is the part that jumps ahead a little bit to the second lesson, but we're going to see it all today anyways. But so if your teacher is producing an interference pattern on a wall, how can you identify whether it's a single or double slit? So we can do that part for now, single or double slit. Obviously, if it's a single slit, it's going to have that single slit pattern of a double wide in the middle, and then this pattern. And if it's a single slit, and if it's a double slit, it's going to have, roughly speaking, even bright bands, right? So if it has a central large maximum in comparison to the others, it's a single slit. If it has equally spaced fringes, it's caused probably by a double slit. The multiple slit you're going to see in a minute, and it was basically, if the resolution is really good, you can see like really clear spacing between the fringes and so on. It was likely produced by a multiple slit pattern, or a multiple slit apparatus called a diffraction grating. So I'll be showing you pictures of that shortly. So we're talking about wavelets, Huygens wavelets, and saying, okay, we can explain this pattern, and the math that follows here. I'm saying brace yourself, whatever. It's not that big a deal. It's just basically, we're going to reason out the idea of this. And in fact, actually, you'd have to brace yourself more if I was going to be more thorough on the development of the math here. I'm showing you roughly the idea of it, and you have to go through a lot more steps to really draw the final conclusions. But I'm just going to show the idea of it. So we have an idea of why it happens. Okay. And so we can think of the interference at any spot as being the combination of a whole bunch of waves from a whole bunch of spots in that slit opening. So a wave from the very top, away from the bottom, away from 3/4 of the way up, away from 1/4 of the way up. These are all pairs, and we're going to be pairing them up like that when we analyze this. So we're going to say like the top with the bottom, and we're going to say with the top quarter with the bottom quarter, and so on. And we're going to see how they pair up. Okay, so this is for the very center. And because we're talking about the very center, all these path lengths are identical. And so everything is constructive interference. There's nothing else going on. It's all constructive interference. So it makes sense that center section is bright, because they're starting in phase. They're traveling the exact same distance. They're going to arrive in phase. Okay, so the center maximum is super easy to explain. What we do next is we start to go off to the side, okay? I'm trying to decide if I want to show you this one or this one next. Let's take a look here. Basically, if we go off on an angle, okay, this diagram here showing that basically if you look at the path length for the bottom ray and the path length for the top ray, they're intending for this line here to be sort of parallel to what you're landing on eventually. There's a lot of approximations in this, but basically you can see that this, as you go an angle out, this path length becomes, this much longer where I'm wiggling the mouse there. So that's the path difference, okay? So they're saying, okay, well, if you had, which part do I want to focus on here? The first dark fringe below the central maximum. They said it occurs at such an angle that the path difference is going to be one wavelength, and we're going to analyze out why. Okay, so we're going to say, okay, for the first dark fringe, it's going to have an angle so that the path difference is one wavelength. Okay, so right there, one wavelength, and then, that's probably, I hope that's a bit surprising for you that we're talking about destructive interference when we have a path difference of one wavelength. And so the rest of that paragraph talks about why. Let me jump to my analysis here to show you. Okay, so this is a path difference of one wavelength, and then if you look at the analysis here, they basically go through the idea of, it's like if you looked at the bottom one and the middle one, then this is a no phase change at all, and then this is off by half a wavelength. That's what that's there for, right? So the bottom and the middle is destructive interference. And then one up from that, you're like one up from the bottom and one up from the middle, that's destructive. And then two up and two up is destructive, and three up is destructive. You got a whole bunch of pairs of destructive interference when you're at a one wavelength there. That means there's a whole bunch of pairs of half wavelengths different. So the sine of the angle equals the wavelength over the width right here. That's going to help you figure out an angle for destructive interference. Okay. Does it say something similar to that here? Like it says, each of the wavelets traveling the top half cancels from the bottom half, essentially they're saying, right? Like exactly like I said. So the next step is to say, okay, well, what about constructive interference? And so constructive interference, I'm going to show here, trying to reason out, roughly speaking, that if we had a path difference of 3/2, okay, then if you look at the bottom third and the middle 1/3, they're going to be off by half a wavelength. Okay, so the bottom third here and the middle third, they're going to be off by half a wavelength, a 1/2 and a wavelength. Right, they're off by 1/2, so that's going to be dark. But the top third and the bottom third, right, they're off by a full wavelength. So you've got some dark and you've got some bright pairs, right? And so basically you're going to be at a percentage of the brightness. You're going to be 1/3 the brightness. So what we're getting is an explanation as to why we have a bright center section, and then the next section is like 1/3 the brightness. Okay. Obviously, we could analyze this a lot further, but I think we're doing all right. And then we get to two wavelengths, and you're like, okay, so basically what I'm getting at here is that we could analyze the heck out of this and make really good predictions about light based on wave properties. And that's our main goal, is just to gain a healthy amount of knowledge and respect for this weird connection between the two, right? That light is certainly showing wave properties. So this talks about the constructive part being a lambda over W and a 2 lambda over W. Like basically, like before, we found there's a sort of a numerical pattern for when we have constructive or destructive interference. And so we had for the destructive part, we had the lambda over W, sorry, that was the first one, right? And then the constructive part was the 3/2 lambda, as I showed there, right? So this is just summarizing those results, really, is all that page was. So we have these like 2 equations now to do with, you know, the single slit interference pattern. So we could do this. Oh, let's go here. So single slit interference pattern. Oops. Single slit. That nice and easy to find, single slit interference. And we've got some new tools that have to say, oh, it's a single slit interference pattern and it has a wavelength of whatever and a width between the slits of whatever, and you're looking at whatever number. You could predict what angle for dark fringes, and you could predict what angle for bright spots. You just plug in numbers, solve. So this one is for destructive interference. Which of course is dark, and constructive interference. Over here, and still, like I said, strangely, it's sort of the opposite opposite effect, right? As far as the yeah, there we go. I'm just gonna copy that. The 1/2 business. There we go. Okay. So some amount of reasoning and understanding. That's a summary page there. Actually, it probably would have been easier if I had a grab from there, but let's keep going. So we've got that. Notice, as usual, the bright sections start as like 0 and then 1, 2, and so on, right? So the 0 and then the first brightness and then the second brightness. And then the dark ones are like 1, 2, 3, because if you're starting with bright, you know, they decided to number it that way just for simplicity and the same as what we've done in other realms of math and science. So if we continue on with this, these ones that we just put on here aren't the most useful versions of it for what you're actually measuring with light. And so we make it a little more useful because, you know, measuring the length to the screen and the distance over is the easier to do stuff, right? So basically, it's pretty easy, really. Like, well, sine of theta is obviously the opposite over the hypotenuse, so the L must be that. But this part right here, okay, so let's just explain what they're doing here. So the small angle approximation means that for small angles, which you typically are going to have pretty small angles, if you're looking at an interference pattern and you're far away, like as long as the L value is a lot greater than the Y value, then even though that's truly where L is, this length here is very, very similar, very close. I gotta trying to control the screen here and it's not letting me. Or I think I just need to change my battery. It has finally died. Well, not finally, it died pretty quick. Here we go. I think I got the school to order me some. One sec here. Battery. All right, see if that works now. Yes, all right. So the small angle approximation is that this L here is really similar to this L here. Okay, that's why we're saying sine equals opposite over hypotenuse, right? but the hypotenuse and the adjacent are very, very similar. Right? Ugh, my pen's working, my hand's not. So the adjacent is really similar to the hypotenuse for that small angle. Okay, so that's just a weird little approximation thing that we need to be okay with. So then with the earlier equation, we're saying, okay, so sine theta equals the n lambda over w, so that equals the distance to the side, yn they're calling it, over the length. So for example, for the first minima, for the first dark interference, this is destructive interference right here. My pen is not working the way it normally does. It's like it's writing before I even get to the screen. So anyways, the first minima, the destructive interference part, that is what we end up with, the 1 being there. And so computer difficulties here. We end up with something like that, right? So they're saying y1 is the delta y over from there. Just developing a formula that's going to work for us. Okay, so you can see the steps there that this was justified basically, right? So they're saying, okay, so instead of just having this one, we also have this one, and and so on, right? So why don't I copy that screen, that page in, maybe instead of the stuff that I just had, or as well as, whichever. So again, I wouldn't want you to stress out about trying to memorize these equations. I just want you to recognize, and be aware of the fact that these relationships are justified and you can use them, right? So you can refer to an equation sheet and use the results that we worked hard at gaining an understanding as to why they are what they are. The numbers are justified there and so on, but yeah. So a little bit redundant, maybe. I probably can just get rid of the first part, but oh well, it's there anyways. So let's just see it in action here, those equations. Okay, so it says, when light of a certain wavelength, so they gave me wavelength, I'm obviously going to make note of that, so I remember to use it, is shone through a slit. So it's a single slit. Notice that it is a single slit. I have to use cursive here so it doesn't look so weird. So single slit, and the patterns created on the screen, such as the first dark fringe. So the first dark fringe, that's n equals 1. So that's that next part. And of course, they said it's an angle of 8.6 degrees. Right? So you just pick out the details of what the heck we're looking at and what they gave us and what we're talking about. And the single slit, fact that it's a single slit, means that we're going to use single slit equations, right? And so they're giving a picture here first, whatever, of it. Wouldn't necessarily need to do that, but that's just for helping you understand what the heck we're talking about. But what I was hoping to go to next here was this, right? So that's the single slit equation that has to do with angle and wavelength and W, the slit width. We're using W now for slit width instead of D, the distance between slits. Okay. Anyways, numbers go in, and then solve, or solve and put numbers in as usual. But it's really not any more than, I'll jump back to it here, it's not any more than this level of question, right? The easiest level, where I give you all the values except for 1, you're just solving for the missing piece. So I hope that helps you know that you just need to be able to work with those things. I was going to go to the view here. Does anybody need this page a little longer?
Just a minute longer, please. Sorry.
Of course.
Okay, I'm good, thanks.
Right on. All right. So number 2 here. Let's go view. Zoom page width. So what are we given? Unknown wavelength. So we're probably going to be asking for that. Yep, there we go. It's on the bottom. Calculate the wavelength, right? And so in here, it's going to be like wavelength equals question mark somewhere. They tell us we have a slit width of 0.600 millimeters. So you're going to have a W value somewhere. So W equals the distance from the center maximum to the second dark fringe. Oh, by the way, do you notice in the previous lessons in the homework and that I didn't always convert to meters, right? If everything was given in centimeters, like in this question here, it's everything's given in millimeters, then you can often just work with that. Just know that you're going to be getting your wavelength in millimeters if you did work with millimeters, and then you have to like maybe consider whether you want to convert to like nanometers like normal or whatever, right? So this, I would say I forgot to mention it, but in I don't know, 3 or 4 days ago, whatever it was, homework solutions, that would be maybe the first time in the course where I wasn't rigidly always switching to meters, kilograms, and seconds. It just wasn't necessary, right? If you're getting an answer for something in centimeters and you're given centimeters, we'll just work with centimeters. So it's when you have like joules for energy, and then you give you like a length in centimeters, be like, well, the joules number is based on a meters unit, so you have to switch, right? But you don't. In this case, you don't have more complex concepts like energy and momentum and things like that, so you don't have to switch. End result here, what do we have? Distance, the distance from the central maximum to the second dark fringe. So we're talking about an n equals 2, and they gave us a value. So so they gave us the value there, the 4.2, and the screen located 2.8 meters away. I think I should have had a n equals 2 in here too, right? I'm guessing, and so on. So you're saying, okay, there's the picture of it, great. We know what we're looking at, and they're going to have an n value of 2 in there eventually as well. So again, there's the formula that's to do with the situation we're talking about. Obviously, I could have just gone to the equation sheet as well, right? Right here, and said, okay, we're talking about dark fringes and so on. So that's the one they grabbed, and here it is. Numbers plug in. Solve for the missing piece. So I'm going to leave it at that for a little bit, assuming someone might want it still.
Yeah, I'd like it still, thanks.
Yeah. Just keep in mind, I don't know what you're doing there, like at home taking notes, but you're making note of either on paper or in your thought process, in your brain for this. You know that I just have to recognize the type of situation and then pick the equation from the equation sheet and use it.
Sorry, I missed what a couple of the given pieces were.
The given pieces up here were, they gave us the W, they gave us the distance over, I'll move this slightly more like that. So you can see like the distance from the central, you know, the perpendicular bisector, if you will, but the central line of the situation here out to the second dark was 4.3. So that's your Y value and so on. Distance to the screen is 2.8. And so on.
That's good, thanks.
Good. All right. So then numbers can just go in and you get results. Try another one, just so you can recognize these things. So we've got calculate the width of the central maximum when violet light, so they gave you a wavelength. So I'll show that. Is shone through a 3.4 times 10 to the negative 5 meter wide slit that is 1.25 meters away. Notice we're given like meters and meters there. This wavelengths in nanometers, so we're going to be converting that to meters. So we have meters working with meters, of course, right? At some point. So they're not showing it yet, but you'll see in a second, I suspect. So we get the L value and the distance to the screen, that is the L, and then the slit width and the wavelength and so on. So as usual, they're showing a little picture of this. So the central maximum is a little bit of a weirder, different style of question, but they're asking for like the width of the central maximum, and so they're going to point out that you're talking about like the distance to the dark spot here, right? Call that like the Y1 or whatever, the dark spot. You're going to have like 2 of those, right? So you're going to have Y1 to get to that dark spot, I believe is what that's going to look like. So they are, oh, they had, sorry. They ended up using the actual delta Y formula. So between adjacent nodes. Anyways, I think you could calculate the way I was thinking of it, where you'd get the distance to the first dark and then double it, would work as well. So you see the wavelength, the length, and the width in there, just like there was. So they're solving for the delta Y that we want. And notice, of course, like I said, the 405 nanometers business. Nanometers means times 10 to the negative 9. And so we're looking at 405 times 10 to the negative 9, or I think it was probably written as 4.05 times 10 to the what? This thing's too smaller now than it was, and so I want this thing to be too bigger, which means -7, because -7 is too bigger than -9, right? So that's why they have that -7 in there. Whew, got it. Okay. I find that delta Y thing not super clear myself, but so that, see the central maximum. So the delta, I don't know if I was using it as a delta Y, but they're saying there's the 1.5, right? And then we're talking about 2 of those, like I was saying. So I guess it is the same as what I was thinking when I wrote this, the 2 of them there, right? So this, when I wrote Y1 and Y1, was actually delta Y. Delta Y. And they're showing 2 of them. I'm just thinking here, like, why wouldn't we just use that? Oh, I guess because the N is a 1, right? Like it's so subtle of a difference. That's really all we're talking about, right? So to me, like I was very much just going to go ahead with this one and use N equals 1 and then say Y and then do 2 of them. So you might benefit from that as well, if that makes sense. And we could just do this. Where's my file here? Right there. So the idea is, oh, not clone. I don't want to do that. I want to paste. So 4, of course. And then the rest of the numbers go in as normal, right? Yeah, all the numbers would have just gone in like normal. And you get your Y1 equals 1.5 centimeters. And then of course times 2, like I had already said, I don't see the difference. I don't know why the delta Y would be necessarily formulated. But anyways, does that make sense? Just using the equation that we've developed and putting numbers in. So what do we have here? A helium neon laser with a wavelength of 633 nanometers. Thank you very much. You gave me some numbers. I'll use those. Shines through a single slit. So right away, of course, again, when you're looking at questions I have to do with this, of course, it's always single slit, right? But later on an assignment to do with this, you're going to think, oh, I have to recognize which equation, and that's the key. So it gives a width, so boom, there it is. So there's the numbers they gave us. What's the maximum possible number of minima visible on a screen? Yeah, single slit the width of that onto a screen. What's the maximum possible number of minima visible on a screen? I'm not following exactly what they mean here. Let's just follow. Let's just look at this and see what they're doing. So they're saying the maximum number of minima means, maximum possible for n. Trick here is to realize that the maximum number, the maximum angle would be 90 degrees. Huh. Yeah, okay. I guess it was just a very different style of question. I just forgot that that one's in there. So it's kind of a, once your angle goes to 90 degrees, obviously you can't go any more than that, right? So the most you could have in this formula to do with right here, to do with minima, yeah, dark fringes, right? If you set that to 90 degrees, you can figure out the n value that corresponds, which gives you the maximum number of dark lines, I guess. Kind of different style of question, but makes sense once you think about it. And honestly, what just happened there is kind of what I'm hoping you're going to be or have been doing with the solution sets that I've posted too. Like you look at a question, you're like, oh, I don't know what that means. So you can sort of look at the solutions and think, oh, okay, and learn from it. Right. So if more of that needs to happen from the motion unit prior to Thursday to build towards success, you know what you need to do. Right on. So that's just a picture of it, but no different than what we've seen before. So single slit interference. Acknowledging that it exists, which not everybody does. And as usual, of course, you could do this with waves, right? Water waves do this, so you can calculate it and it all works and makes sense. Or cut to the chase and do what we're really trying to focus on here is that light has these wave properties. If we had more time, you would separate this out. You would have done this with waves and then later on do it with light. I prefer the idea of doing it together because the comparison between the two is more obvious. So anyways, but it's the exact same equations and work. So that's the stuff I want you to do there. So just about diffraction gratings and then a neat link to money safety features. But diffraction gratings are, we don't need that stuff there. Diffraction gratings are when you have a whole bunch of lines. Okay, so it's a large number of equally spaced parallel slits that act as individual light sources. So this whole act as individual light sources isn't new. With a double slit, you have one light source behind the slits, and then the light comes through the two slits and acts as like individual light sources that are perfectly in phase with one another because they're literally from the same light source. So a large number of equally spaced parallel slits we're talking about. They can have line densities exceeding 10,000 lines per centimeter. These things are like precisely drawn out with like lasers and AutoCAD and robots or whatever, right? They're produced, and so they can have 10,000 lines per centimeter. To convert that to an actual distance between the slits, right? The D value, the distance between the slits, is we're going to do that down here, I guess. But this is line density, is number of lines per distance is your line density, right? So we're talking like 10,000 lines divided by 1 centimeter. Okay. Down here, we're going to be saying, so if we have a line density of 10,000 divided by 1 centimeter, so let's put in 10,000 divided by 1 centimeter, then if I want to know the distance between the actual slits, then distance divided by number of lines, in this case 1 centimeter, divided by 10,000 is going to give me the distance between the actual slits, between the gratings. Okay. I may as well show you right now while we're at it. That is the same as the D value we're used to seeing for the distance between two slits. Okay, so the D value, it's the same as that D value in the previous equations. So we're not going to analyze the math as to why that's true. I'm just going to tell you it's true at this point, and then later on in a future physics course, if you go on to in this stuff, you'd probably see a full justification as to why the double slit patterns work, equations work. But that is for another day, possibly. So back to this here, of course, the reason we do this is because they produce super bright, super sharp double slit interference patterns. Okay, so with the increased number of slits, basically you're getting more constructive interference and more destructive interference. And so you're getting this basically a much more resolved image. So you get super bright, super separated lines. And so they're really easy to measure. And so if you're using these things to determine a wavelength of light, for example, the measurements are easier because everything's more focused and intense and separated and so on. Okay, so it says there, the equations for analyzing interference patterns are the same as those of the double slit, right? Sometimes rather than being given the distance between the gratings, you're given this density, so you have to get the distance between the gratings. But again, like I'm saying here, this is a pretty big statement, right? The equations for analyzing interference patterns created with diffraction gratings are the same as those used with double slits. And I suspect there's a proof somewhere, proof at some point, let's say. If you're going on in this and you want to understand fully everything to it, then that would involve a little bit of legwork there to show that. But it's only so much time for us right now. All right, so we're going to be referring to our double slit interference equations. So modeling the behavior I'm looking for from you, you're like, I'm not stressed about this. I just go up and I look at my double, 2-point source interference patterns. I'm going to make that even a little bigger and more obvious 2-point source interference patterns and the equations. So all these equations are going to work for this diffraction grating. Okay, so we'll refer to those with minimal stress. So first of all, the line density thing, I already showed this, right? So you're given this line density of 10, or this one has 1,000 lines per centimeter. So if you want to know the D value, the distance between the grating lines, the D value, then you would just be like, wow, there's 1 centimeter divides into 1,000 pieces, right? So divide into 1,000 pieces to get a spacing of 1 times 10 to the negative 5 meters. So that's an easy calculation that goes along with a lot of these questions. They're going to give you line density quite often, simply because that's how they're manufactured, how it's when you buy a diffraction grating, you buy it based on what line density you want. Okay, so that's no different than what I showed on the other page, really. So here's a question. So a beam of light, monochromatic, meaning like only one wavelength, and so probably going to be asking for the wavelength. Yeah, we're looking for the wavelength since they didn't tell us the value. So it's shined at directed at, they're using directed at, so they don't have to say shined or shone or whatever. Has a line density grading of 5,000 lines per centimeter. If the angle of the second order bright fringe is 28 degrees, so we're, obviously it gave us angle 28 degrees and M equals 2. Notice why it's M. We've got a bright fringe, and so it's an M. Right? So we've got an angle, we've got an M, we've got a wavelength we want, and we've got a D value. So you go and you look at your equations, you're like, I want one with an angle and a M and a D and a wavelength and so on. You're like, hey, that's going to work. So I'm just going to actually screenshot that. Obviously, it's on this page already, and the page we're going to work on. But just to show the size, that's the name of the game here. Use the equations. That's the equation that comes out from the equation sheet to do with that. obviously they're gonna do the line density thing first, get the D value first, right? So you're kind of left wondering about the D value. So first you do that. It's 5,000 lines per centimeter. So 1 centimeter divided by 5,000 lines gives you the spacing. And the equation that you use is that. So I have there, obviously I've been doing this anyways, but yes, of course, just pick that from your equation sheet. Plug numbers in and solve, or they're going to solve for wavelengths first. Of course, they're going to multiply D on both sides and divide both sides by M. They get this. And then they plug their numbers in and calculate the wavelength. Okay. Notice that this means times 10 to the negative 9. So when they went from this step to this step, it was actually like times 10 to the 9, right? Because you have a times 10 to the 9 and a times 10 to the negative 9 canceling out. So basically, yeah, that gives you 470 when you do it. But if you're wondering about the prefixes and numbers and so on, let's do it again. Light from a laser with a wavelength of 720. So if I had this covered up still, of course, I'd be like, oh, of course they gave us wavelengths. So guess what? It's listed. Line density of 1200 lines per centimeter. And of course, you may as well just point out we're going to get D equals the number of centimeters divided by the number of lines. So that's going to happen down here is the first thing. Yeah, put my screen back. Don't know why. There we go. So that gives a 0.0083 centimeters. What else do they give us? If the diffraction grating is located 50 centimeters from the screen. So they're saying, oh, well, that's an L value, right? So you go back to your equations and be like, oh, was there an L? Yeah, there was, right? And we're talking about bright fringes as well. So bright fringes, so we're going to use an M equation. So they want the distance. And so our formula is that one, which was on the formula sheet, of course. The delta X lambda L over D. Okay. So no manipulation needed at all, just plug numbers in and calculate. So what I didn't talk about earlier here, I just realizing I kind of missed it, was we want distance between adjacent fringes. When we did that one, we had done like X1 or X2 take away X1 business, right? But we ended up developing a formula for delta X, and so that's why I chose, that's why the one with delta X is being used, of course. Okay. What is this one? Light. Oh yeah, this one's good practice for you to you can do later on. So they're saying if you have white light, okay, and it's diffracting by different amounts because different wavelengths will diffract by different amounts, end up with first order fringes for red, orange, and yellow. So if you're going to see red, orange, or yellow, first of all, you have to realize you're looking at bright stuff, right? So you're looking at seeing red, seeing orange, seeing yellow. So we're talking about brights. We're talking about constructive interference. So I'll just put an arrow down to there. And they tell us line density. They tell us because 1 centimeter is this many lines. We have angles, and we want wavelengths for certain numbers. So again, we're looking at that formula. So obviously our line density thing would still happen first. But yeah, you're just going to plug in numbers, right? So what are the colors associated with these wavelengths? That allows you to get the wavelength for red, the wavelength for orange, the wavelength for yellow. The wavelength for red corresponds to 30. Wavelength for orange corresponds to 35. Okay, so you can picture how scientists were able to measure wavelengths of light pretty easily. If you have a diffraction grating, it's pretty easy anyways, right? So solve for wavelength, that's what we want, or put numbers in and then solve for wavelength. But either way, numbers go in, and you get the wavelength. Okay. So basically, that's worked out, and then the process again for 35 degrees, the process again for 45 degrees. So I'll reveal those, but you might want to do those yourself from scratch and make sure you're able to do that. So they're ready to go for later. So this is in the back of 124, fog machine going. This is what the diffraction grating looks like, a little piece of glass with a little border around it. And then when you look at it close up, you can actually sort of see little spots where you can shine the laser and know that you're going through a certain diffraction grating. So I was trying to show the idea of the three, like if you picture this being a surface of water, and you'd have like a wave here and then a spot where there's destructive interference and so on, that you get this like three-dimensional look. You can actually start to see it there, right? So the interference pattern on the wall ends up being this like just a sequence of light and dark bands, but it really is like, you can see there too, like it's this wavy kind of thing going on between there. Like if I look back at this last slide here, picture that wave as waves, water waves, and then picture, based on light intensity, you can picture that same pattern being there. So if this was a single slit, is this one a single slit? Yes, it is. I can tell because that center section is so bright, and then it goes dark and then a less bright section, and then dark and then a less bright section. So you can see that single slit pattern, just like we looked at in the previous lesson. Okay. When it arrives on a wall, of course, it just looks like this right here, like just barely see it there, but we saw it earlier in the previous lesson. But the diffraction grating, so I was super happy to get these pictures to be as good as they are. Honestly, really, I was like, wow, that'll work once I got the pictures and so on. This is the kind of thing you get with diffraction gratings. Much more defined, much easier to show, much brighter patterns and so on. And then of course, easier to measure. Okay, so you get much better contrast and brightness with diffraction gratings, and that's why they exist. That's why we talk about them. Okay, so the questions to do with diffraction gratings, again, just like we did in the lesson. Identify the type of question, identify the variables, pick the equation, plug them in, solve for the answer. Okay, so that's long enough for you to jot that down, I hope. And there is a neat little connection to money. So these slides are pulled from a different presentation that I've done, like a different lesson that I've done for a different class. So you'll see some redundancy here when we get to it, but basically it's like designed for the layman person, not necessarily a grade 12 physics student, right? So what do these three things have in common? Light, waves, and money. And so of course we've been focusing on the connection between light and waves, but then the money is kind of a new one for us. So of course, it turns out that light behaves as a wave, as we've been seeing lots and lots of times, even though light is really, I'm going to put maybe in quotes here, light is really, because this is what people tend to think, right? Really particles called photons flying through space. We have these two competing ideas that we've been talking about. So since light behaves as a wave, we can look at wave patterns, diffraction, circular patterns, and so on, right? So waves do something called diffraction that people don't even necessarily notice, and light certainly does that too. And so that's the key here. Light does this too. So what does laser light look like shine between two pencils? Of course, we know exactly what it looks like. We just talked about it in the previous lesson. So the light spreads out like that. This is where the two files I think come up. So notice the dark. Remember I started saying I had two of these somewhere showing it. This is where it was, I think. So notice those dark spots. right? That's spots where light is canceling out. And so I'm pointing out that, of course, waves do that too. So these spots here where there's no waves, it's because this wave and this wave, the two angled waves are canceling out, right? An up and a down wave canceling out. So that's destructive interference. Waves do it, light does it. This is a nice little drawing here to show the idea of a wave that is, in phase would be bright. So that'd be the middle section here. But at this dark spot right here, you must have destructive interference like that, an up and a down canceling out, right? So from two slits, or two light waves from two different locations in the pencils. I'm saying that was that slide we talked about, the bottom third and the top third and so on, right? Because we're talking about single slits here, because that's easy for people to produce. So that's just a recap of like what we talked about in this class, right? But the connection that I want to show you, just because it's neat and you can actually use it to check to see if money is counterfeit or not, if you're interested. And someone's buying something from Kijiji or something like that, they're giving you a couple $50 bills, make sure they're good. Okay, the clear section of maple leaf is actually pretty cool. It's a diffraction grating, but it's a pretty neat and carefully defined and designed diffraction grating. So instead of just producing an interference pattern like that, it produces an interference pattern that tells you what kind of money it is. So I'll show you. So shine a laser through there and then see what it does on the wall. Or you can actually even just look through it at, say, a bright light, but I'll show you that in a second. But this is when you shine laser light through it. And so from a $20 bill, the laser dot hits the wall and then light diffracts out in a very, very defined pattern of a $sign, a 2, and a 0, showing us a $20 bill. And then you can do it with red light or green light and so on, just a couple different pictures to give you a feel for what it looks like with lasers. If you don't have a laser at home, which no one said they managed to find one, you can actually just look through the metal, the clear leaf part on the money at the point of source of light on your phone. Your flashlight on your phone works well, or if you have Christmas lights nearby, they work well as well. So this is a picture on my front deck 4 Christmases ago or whenever it was. And you have right there, you can see I was looking through, you can tell what kind of money I was looking through if you look carefully at it. $signs and a 5. Yeah, you got it. So that was a $5 bill. And the other thing that's kind of neat is notice that the pattern is bigger for the orange than it is for the blue. And with the blue, you've got a smaller wavelength. So you've got less diffraction, you have the smallest pattern. The red's even bigger because it's the largest wavelength, the most amount of diffraction. So it links back to what we talked about how much diffraction occurs relative to the wavelength, right? Remember we looked at waves and we saw like the narrower the gap you're going through, the more diffraction there was. And so here's light doing exactly that. Again, add it to your long list of wave evidence of light, or evidence of wave nature of light, I should say, to be more clear. Okay, and so if you've ever played around with these kind of things, the dollar store has them, corner stores have them, little laser pointer toys or whatever. These little interchangeable tips are diffraction gratings, and it can make like the shape of a mouse because people play with it with their cat, or it can be a little arrow you want to point which way for someone to look on a screen if you're using it as a presentation tool and so on. So they're diffraction gratings that make that happen. They're not just a little cutout of a mouse and it shines through. Like that wouldn't work properly. They're actually a diffraction grating designed to make constructive interference happen at specific spots. So that is it. Okay. So I will, of course, always save all this stuff, PDF it, post it up for you, and I'm around, for a bit longer here for help directly during class time. I'm not available today for the help session though, but I'll be around tomorrow for help session. Okay. I can do a help session later on though, if that's needed. Like if there's emails for help, I can just initiate a screen share to make it easy. So just not at 1 o'clock this time. All right.
Thanks.
You're welcome. Very welcome.